Welcome back everyone, welcome back to Stelzer's Science. This is part 2 of my two-part series on the Unit 3 exam review for AP Chemistry. If you have not checked out the MCQ, go and check out the MCQ. Make sure to like, subscribe, hit that bell notification icon. So let's go ahead and get into it. We are into the FRQ portion now. Let me go full screen. And let's get into these FRQs. Two FRQs, one long, one short. 20 to 22 minutes for the long, 10 to 12 minutes for the short is the time frame for your exam. So, gotta flip this, make sure I can write on it. Alright, answer the following questions about elements in group 16 of the periodic table. I don't have my periodic table or my formula sheet with me. Hopefully I don't need those. Alright, using principles of atomic structure, explain why the atomic radius of Te is less than the ionic radius of Te 2-. So this 2- means plus 2 electrons. So the reason why the Te 2- has a bigger radius is because of it has just more stuff. There's more electron repulsion, or you can say electron shielding, because that's what electron shielding is, in the Te 2- ion. And then for an added bonus, they both have the same amount of protons. Both have same protons. I'm going to go one size down. It's a little, marker's a little too thick. That's a little better. Okay, photoelectron spectroscopy data for the 1s sublevel. So this is only the 1s sublevel of Te, and the 1s sublevel of O are represented below. In terms of Coulomb's law and atomic structure, explain why the peak for O is positioned so far to the right of the peak for Te. That's because Te has more protons. I don't know if you guys can hear that lawnmower, what seems like right next to my ear, but I can, so hopefully that won't show through the video. So more protons. So I wish I had a periodic table. I guess I'll just go to the old phone and look one up. Periodic table. So Te is element number 52. Oxygen is element 8. Te has 52 protons in its nucleus. Oxygen has 8. So that means Te is going to hold on to its 1s level way more than oxygen is going to hold on to its 1s level. So we have to give an explanation, and the explanation is simply that tellurium has more protons in its nucleus, and then that's 52 versus 8. So let's shout out Coulomb's law. To Coulomb's law, the more protons, the greater the force of attraction. Alright, C, TeO2 reacts with SeF4 to produce SeOF2 and TeF4. The unbalanced chemical equation for the reaction appears below. Give the value of each of the following coefficients in the balanced reaction. So, alright, so let's just start balancing. Let's make this one a 2. Let's make C a 2, just so we can balance the oxygens. We have 2 oxygens on the left, 1 oxygen on the right, so that makes the oxygens equal. Now the seleniums are unbalanced, which means we would need 2 of these. So now that we have 2 seleniums on this side and 2 seleniums on this side, and is everything else balanced? That means we have 8 fluorines, we have 4 fluorines from here, 4 fluorines from there, so 8, 1 tellurium. We're good, so it is 1, 2, 2, and 1 for the balanced equation. Which structure, B, C, or D, minimizes the formal charges for each atom in SeO2F2? I also skipped the little thing up there. This lawnmower is so distracting right now. I gotta keep going. Alright, so we have 3 compounds that contain elements from group 16. Are those 3? Here are the possible Lewis dot diagrams. Which structure, B, C, or D, minimizes formal charge? Alright, formal charge is equal to the valence electrons minus the dots plus the dashes. So we got to check B, C, and D and see which one minimizes those formal charges the best. So first off, I'm just not even going to check the fluorines because the fluorine is literally bonded the same in every single one of those, so there's no differences. It's not going to be the fluorine that causes it to have a different formal charge. Let's check, let's just go one by one. So oxygen has 6 valence electrons. In this B, it has 6 dots, 1 dash, so it's a -1 on both of those oxygens. Selenium has 6 valence electrons. Selenium is also in that group 16. So 6 valence electrons. It has 4 dashes, so +2 formal charge. For C, oxygen, so we know that this one's -1 because it's just like the other ones. Oxygen has 6, 4 dots, 2 dashes, this one will have 0. Selenium 6, this one has 5 dashes, so it's going to be +1. And for the last one, selenium, this one has a 0, this one has a 0. Selenium 6 minus 6 dashes plus 0 dots is 0. It looks like D minimizes formal charge the best. And for the justification, we justified by doing the math. D, its formal charge on all atoms is 0. A student proposes that the energy of the Se to F bond in the structure in diagram A is equal to that of the Se to F bond in the structure in diagram D. Do you agree or disagree with the student's claims? Justify your answer. So we have a fluorine bonded to selenium here. We have a fluorine bonded to selenium here. It's the same atoms bonded to the same atoms, and both are single bonds. I think they're both going to have the same energy. So I'm going to agree here. Energy and length are inversely proportional, so as length gets bigger, energy gets smaller. The length looks like it's going to be the same because it's the same atom. It's fluorine bonded to selenium in both cases, and both are single bonds, so therefore they should have the same energy, so agree. Both are Se to F single bonds. Alright, the dipole moment in SeF2 is non-zero, diagram E. Identify its molecular geometry and explain how its geometry and the polarity of its bonds results in a non-zero dipole moment. Okay, so SeF4 in diagram E. It has 4 bonded atoms in 1 lone pair. That is seesaw. That's the one where we kind of had like 2 legs, and then we also had like the seesaw, and then we kind of had like the lone pair on top. So it is a seesaw. You just kind of either know that, you don't that, or you don't. Did you memorize Vesper? Did you not memorize Vesper? Why does it have a non-zero dipole moment? It has that non-zero dipole moment because it has an unbalanced lone pair on the central atom. So it has to have a dipole because there's one lone pair here and there's no other lone pair to like balance it out, so there must be a dipole. It must be polar. The melting point of SeOF2, which is done diagram A, is greater than the melting point of SeO2F2 in B, C, and D. Identify the types of IMFs that the two substances have in common. Well, they always have LDFs. And they all also have dipole-dipole. It's pretty obvious why A has a dipole-dipole. It has an unbalanced lone pair. B, C, and D don't. However, B, C, and D's dipoles are going to be dipoles because they are unbalanced in like what the selenium is bonded to. It's bonded to like oxygen over here, but fluorine over here, and oxygen and fluorine are not the same. They have slightly different electronegativities, slightly different distribution of electrons, so therefore they're going to be slightly polar in the sense that it's polarity based off of unbalanced of what it's bonding to. But they both still have dipoles. Explain the difference in melting point based off the types and relative strengths of intermolecular forces. So they both have the same types of intermolecular forces, but A's dipole-dipole is going to be way stronger than B, C, and D's because A's dipole-dipole is based off of its geometry. A's dipole-dipole is stronger because it is due to its geometry. B, C, and D's dipole-dipole, and I just said this, is just due to the fact that it's not based off the geometry. The geometry is tetrahedral, which can be nonpolar. However, it's polar just because on one end it's connected to an oxygen and on the other end it's connected to a fluorine. That's still a dipole, but it's not a very strong dipole. A's dipole is going to be way stronger because that lone pair is always there and it's always causing a dipole. That's trigonal pyramidal, which is a very strong dipole shape. So A's dipole-dipole is stronger. And I guess I'll continue. So it has stronger IMFs. Now, keep in mind, for AP Chem, consistency is key. If you do not get G right, if you said like one has London dispersion forces and one has dipole-dipole, then H's answer will probably change. So for example, if you did not get that all three of these experience dipole-dipole, if you said they only experience LDS, then the reason A has stronger dipole or stronger intermolecular forces is because it has dipole-dipole while the other three don't. So your explanation for H would be a little bit different. But they would look, and I'm looking for, is your H answer consistent with your G answer, and is your H answer correct in terms of its chemistry? All right, let's move on to question 2. Oh, I guess I should double check that I got everything correct. Where's my FRQ? All right, 52, 1, 2, 2, 1, structure D, we agree, seesaw, dipole-dipole. All right, good. Did I miss a page? Oh, no, it's over here. Never mind. All right, we're good. We are not on FRQ2 yet. I forgot about this. A student wants to use spectroscopy to determine the concentration of unknown SeOF2. Before creating a linear calibration curve relating the known concentrations to absorbances, the student first needs to determine what wavelength they should choose. A student places the unknown SeOF2 sample in the spectrophotometer and gets the following absorption versus wavelength graph. Based on the graph, which wavelength in nanometers should the student use? All right, so think back to your experiment. The first thing you did when you put in the cuvette with the solution is you're shown the entire wavelength spectrum, and you were asked which wavelength, what absorption should we choose, and we said we wanted to choose a big absorption. So I want to choose that absorption right there. That's what I want. I want the highest absorption, that's going to get the best data. So what wavelength does that correspond to? Now, a lot of people last year, for my students, got this question wrong because they did not know how to read a graph. So it's not at 400. 400 is this line. Can we see that it's right there? You can't just round to the nearest line. That's not accurate. It's also let's see. So these lines, we have 1, 2, 3, 4, 5 steps. So that means it goes every 20. So this would be 380 nanometers. It looks like we are in between, so we want to be there. We're in between 380 and 400. And it looks to me like we're a little closer to the 400 than we are to the 380. So I would go with like 392. So that would be my guess. Or like, I might just say just 390. But let's say 392 nanometers. You have to make an attempt to read the graph to your best ability. Don't get a question like this wrong because you didn't try to read the graph. The range on this question was 385 to 395 nanometers. You had to be within that range. AP Chemistry will give you a range that you're allowed to be in between, but that requires you to still read it to the best of your ability. So many people said 400, but 400 is not within the range. You can't just round to the nearest line. You have to like try your best there. All right, the student sets the wavelength on the spectrophotometer and starts gathering data using known concentrations of SeOF2 to get the absorption versus concentration curve below. At this point I wish you can hear the lawnmower because it's affecting me so much. It's not consistent. It's like and it's just on and off. I wish they would just like mow it and then be done, but that's not what's happening. My goodness. Okay. On the graph above, draw the curve corresponding to the data that would be gathered if the student mistakenly chose a wavelength of 650 instead of the wavelength chosen in part I. Okay, so in part I, we chose 392. This question is asking, okay, this is the line we get if we chose 392. But what if we didn't choose 392? What if we chose 650, which is right here? What if we chose that wavelength instead? Well, that's a way lower absorption. We're not going to get as high of an absorption. Now, 0 is still going to correspond with 0, but everything else is going to be slightly less, and it's going to like lead to a slope that's less pronounced, so a way lower slope. It's still going to be linear. The data is still going to be linear because according to Beer-Lambert law, it's a linear relationship. But we're not going to get as high as absorptions. Okay, there we go. That ends the FRQ. Let's move on to the last one. A student is doing experiments with carbon dioxide. Originally, a sample of the gas is in a rigid container at 299 Kelvin and 0.7 atmospheres. The student increases the temperature to 425. Describe the effect of raising the temperature on the motion of the CO2 gas molecules. Raising temperature means the molecules will be moving faster. That's what raising temperature does. It increases the kinetic energy, and kinetic energy is 1/2 mv squared. We're not increasing the mass here, so therefore we have to be increasing that velocity. So increasing temperature increases the velocity. Calculate the pressure in the container at 425. Okay, so this, right when I read this seemed like a P1 over T1 equals P2 over T2. It is a rigid container, so that means velocity remains constant, so PV over T equals PV over T, the V's get canceled out. Right, initial pressure is 0.7 atmospheres. the initial temperature is 299 Kelvin. It's already in Kelvin for us. Woohoo, we don't have to convert to Kelvin. We are looking for P2, and the final temperature is 425 Kelvin. It's going to be 0.7. Alright, my computer just died. It's plugged in now. I sure hope I'd never had this happen, so I kind of hope it kind of just saved it. I don't know what it's going to look like. We're going to keep going. I really don't want to record this again. That lawnmower is going to drive me actually insane. Okay, power through. Alright, 0.7 times 425 divided by 299 is 0.99498. Rounded to 2 sig figs, since this is in terms of 2 sig figs, it's 0.99 atmospheres. So P2 equals 0.998 atm. In terms of kinetic molecular theory, briefly explain why the pressure of the carbon dioxide in the container changes as it is heated to 425. So the particles are moving faster. Kinetic molecular theory means they want you to talk about what the particles are doing. So the gas particles move faster, and therefore will collide with the walls of the container more frequently and with greater energy. So increasing the velocity, which is what we said what would happen, means the particles are zipping around faster. If they're zipping around faster, they're hitting the walls with more energy, and they're also hitting the walls more frequently. So that's why the pressure goes up. The student measures the actual pressure of the carbon dioxide in the container at 425 and observes that it is less than the pressure predicted by the ideal gas law. Explain this observation. That one went in one ear and out the other. The ideal gas law. Okay, so the ideal gas law does not account for IMFs. So the real gas experience some intermolecular forces. Real gases experience some intermolecular forces, so that will cause the real velocity and real pressure to be slightly less. All right, we're done. That's it. All right, that is it for this video. I hope this helped. I hope you were able to get some insight. I hope you did not hear that lawnmower like I did. I am about to crash out. All right. As usual, if you have any questions, please see me in class, email me. More than happy to answer any questions. Your test is on Wednesday, and I wish you the best of luck in studies. If you want the extra credit for study groups, make sure that is emailed to me. My email, stelzer.sean@brevardschools.org, by Monday evening, because I'm going to be putting those grades in on Tuesday, because that's the last opportunity I have to put those grades in. All right, everyone, I will see you back in class. Have a great weekend. And please close.